chapter 11, we're gonna learn about metal casting processes and equipment. So the casting is categorized generally into two categories, that is permanent mold and expandable mold processes. Basically, expandable means that we are actually consuming the mold each time we are doing the casting process. And permanent mold process, usually the mold used during the casting is made out of metal and can be used over and over again. And because of the molds are expandable, in the expandable mold process, it is much slower compared to permanent mold processes. And we can further divide expandable mold processes into two categories: expandable mold permanent pattern and expandable mold expandable pattern processes. We're gonna take a look at each of the processes and what are their characteristics, what are their advantages, limitations. And we're gonna take a look at what type of casting we can use to produce single crystal components, because usually most of the materials we are producing by casting, they are polycrystalline, but to produce a material that has single crystal structure, we need special techniques, special casting techniques. And at the end of this chapter, we're going to learn about that. So what type of products are made by casting? Common ones: engine blocks, crankshafts, turbine blades, dies, molds, gears, railroad wheels, propellers, and office equipment. So a wide range of application areas are available for materials that are produced by casting. A wide variety of casting processes have been available and they are developed over time. Of course, each of these has its advantages and disadvantages. So in the table in the next slide, in table 11.1, all of these processing techniques that we'll go through in this chapter are summarized in terms of their advantages and limitations. So we're going to learn about sand casting, the most common one, shell mold casting, evaporative pattern casting, plaster mold, ceramic mold, investment casting, permanent mold, die, and centrifugal casting. So you guys, I don't need to remind you, but please also when you are learning, because I cannot show you the videos here, I am sending you a lot of videos in your canvas. Please watch them after listening to the lecture, so when you see the actual casting processes in the videos, and it will make more sense after you learn about it to see how it really looks like. Okay, so we are seeing, as I said, the summary of what we are going to learn. Here the advantages and limitation of each of these processing technique is given to us. For example, can we able to produce complex shapes, or what are the surface quality for each of these techniques? Is it a good quality or a bad quality? Or is it limited by the size? How many number of parts we can produce? Or if what is the quality of the material that we produced? Does it have high strength or ductility after the production? Or does it depends on the grain structure? So what type of grain structures we can get? from all these individual casting processes. Is it an expensive process or is it cheaper compared to other processing techniques? All of these informations are compared here, and we're gonna now by one go through each of these processing techniques. So there are 4 trends that are affecting the casting industry, which is one of them is mechanization and automation of the casting process, because this will reduce the labor, and it also causes significant changes in the use of equipment. So to do that, of course, we need advanced machinery and automated process control systems. And also there is an increasing demand for high quality casting with very close dimensional tolerances. That's why new casting techniques are being developed in order to achieve parts that has high quality. So high quality means surface, in terms of surface quality, in terms of the structure, the properties you achieve at the end, and in terms of the dimensional tolerances you get at the end. These things are important. That's why new processing techniques are being developed to meet these demands. And of course, the development of powerful modeling software, right? Because this type of softwares can help us predict the casting results. It can simulate the result and tell us what type of defects can be possible, what type of microstructure we can get. So therefore we can estimate the mechanical properties we can obtain. So those type of predictive softwares are very important. Okay, so in these images, in the image A, we are seeing typical gray iron casting that is used in automobiles, like transmission valve body and the hub rotor with disc brake cylinder. And in the image B, we are seeing die cast magnesium housing for a camera. And in image C, we are seeing a cast transmission housing. And in image D, we are seeing cast aluminum impellers for automotive turbochargers. So as you can see, casting products are used in wide range of applications. So we can say the major categories for casting is depending on the type of mold, as I explained. So we are seeing 3 different categories here: expandable molds, permanent molds, and composite molds. So what are expandable molds? These are typically made of sand, plaster, ceramics, and similar materials, and mixed with binders to improve their properties. So for example, a typical sand mold will have like 90% sand, 7% clay, and 3% water. So these materials, these mold materials are refractories. Refractory mean they can withstand high temperatures. Of course, we want the molds to withstand high temperatures because we are pouring molten metal. So they have to handle these high temperatures. And after the solidification of the casting, the mold is broken. And in the case of expandable molds, we don't use it again, so cannot be reused. So this expandable molding process divided into two categories: expandable mold, permanent pattern. In this case, the mold is produced from a pattern, and in some cases the mold can be expandable, but we can reuse the pattern to create more molds. And in this case, that is expandable mold, permanent pattern casting processes. If we also need to produce a pattern for each mold during the process, then that is, so we don't use the pattern again during the process. That's when we call it expandable mold, expandable pattern process. So of course the next is permanent molds, and as the name implies, that means we are reusing the molds during the process. And these are made from metals because they can maintain their strength at high temperatures, and the molds are used repeatedly, and they are designed in a way that we can remove the casting easily, because removal is also an important part. You need to be careful in your design that after the casting we should be able to easily remove the part. And this mold is used over and over again. Okay. So because these molds are better conductors compared to molds made out of sand, of course you can understand they are better conductors, right? One is a ceramic, one is a metal, and metals conduct heat much more efficiently, and we learned that the conduction of heat from the molten metal is affecting their structure. So because the metals are better conductors and they are conducting heat at a high, they are removing the heat from the casting at a higher rate, there is a higher rate of cooling during solidification, and which of course affects the microstructure and grain size. So therefore each of these techniques will give you a different type of structure. Therefore it is really important to understand, predict what type of grain structures we can obtain from each of these individual different type of processing technique. Composite molds, as the name implies here, uses two or more different materials. So it can mix the sand with metal, or can use graphite. So different type of, we are combining them and combining therefore the advantages of each of these materials. So what we can do, because we are playing with the composition of the mold, we can play with the rate of cooling. We can control it. Okay, we can improve the mold strength. So these molds can be permanent or expandable. So, but they are made from two or more materials basically, so that we can control the casting process. So all commercial metals can be cast, and the surface finish depends on the mold material. And of course you can understand from that, when you have sand casting, when you are using sand to make the molds, the surface will be rough. And also for sand casting you can do intricate shapes, complex shapes you can create. So when we look at under the category of expandable mold, permanent pattern casting processes, we see sand casting. sand casting is the most common type of casting, and you can produce large parts with sand casting. And it's very simple. You place a pattern. The pattern is the shape of the part that you want to obtain. It makes an imprint on the sand, and therefore we incorporate a gating system for molten metal to flow. And because we need to introduce the metal to the mold, right? And it has a pattern, and we need to incorporate this gating system to the mold, and then we remove the pattern and then fill the mold cavity with the molten metal. Then we allow it to cool down until it solidifies. After it solidifies, we break away the sand mold, which we cannot use it again therefore, and then remove the casting. So these are the common steps of the sand casting. In this table again, all of these casting processes we're gonna learn, they are compared in terms of the typical materials that can be cast. You can see all of them nearly can cast all types of metals. So what are the weights, the limits, minimum and maximum that they can produce? Typical surface finish. For example, I see here investment casting has pretty low surface roughness. That means smooth surface, high quality, and the porosities that can be achieved. Of course, here from 1 to 5, 1 is being the best, 5 is being the worst. So that means that die casting, for example, has relatively low porosity, and because it ranges from 1 to 3, right? So shape complexity. So for die casting, it is 3 to 4. That means it can create low shape complexity. So if it's 1, that means it can create complex parts. It can cast complex parts. And also the same way you can look at the dimensional accuracy. Okay, so in that case, investment casting, permanent mold casting, die casting, these are providing good results in terms of the dimensional accuracy. And of course, there is a limit for the section thicknesses. So because all parts will have not only one thickness, there is going to be a range of thicknesses in a single part. And of course, that should be within the limits of those processing technique. So maximum thickness and minimum thickness information is given to us. And also typical dimensional tolerance. So it means plus and minus. So the error range. Think about it that way. And then information about equipment, pattern, die, labor, and typical lead time, production rate, quantity, etc. All those information is compared for the techniques that we're gonna learn. So this is like a summary of what we're gonna learn. After we go through the lecture, you can come here and look at these tables, and you can find that this is just a summary of what we're gonna learn. And this way you can compare it in a single table. In this figure, we are seeing production steps in a sand casting operation. So of course first the pattern needs to be made. Pattern together with the gating system cores needs to be made, which are gonna be the holes inside our cast metal. So first you do the pattern and sand together, mix them and make the mold, and then pour the metal. Of course, the metal comes from the furnaces, and pour the molten metal and then solidification and cooling. After that we shake out and remove the risers and gates and remove our part, and then if necessary heat treatment is done to obtain the desired microstructure. And of course maybe some finishing operations might be necessary depending on what is the part at the end. Maybe some finishing processes are necessary, so cleaning and finishing, and maybe additional heat treatment might be necessary. And then of course at the last stage we need to inspect for the presence of defects or other dimensional errors basically. So at the last stage is then the inspection. So in sand casting, then what type of sands we are using? And most common one is silica. This is silicon dioxide. We know this is a ceramic material and can withstand to high temperatures. And this is also inexpensive, and it has high melting point. So there are two general types of sand. One is naturally bonded and the other is synthetic. So in the synthetic one is the preferred one in found rice, because you can control the composition of the sand, therefore control the process, control the final structure, microstructure of the cast metal. So properties of the sand also very important, like the sands, if they have fine round grains, these sands can pack more closely, and therefore your mold will have a smooth surface. And fine grained sand enhances also the mold strength, and fine grains on the other hand have low mold permeability. So what is permeability? Is remember some gases like hydrogen can trap inside the cast, so we need to remove them from the metal. And if the sand mold has a good permeability, that means it is allowing the gases to escape, which is what you want. But if it does low permeability, then the gases are much more have a chance to trap inside the material, which will in return cause the defects. Well, the mold also has to have good collapsibility, meaning it should allow the casting to shrink while it's cooling, because see, the molten metal can stick to the surfaces of the mold, and if this happens, then it cannot shrink freely. And in this case, therefore we need a good collapsibility, meaning the mold material should allow the casting to shrink freely when it's cooling. This will prevent the formation of defects such as hot tearing or cracking in the mold metal. What are the types of sand molds? Of course, so we are using sand to make the molds, but then each of those sands can have different characteristics. So one is green sand mold, the other one is cold box mold, and the last one is no bake molds. So there are different type of molds that are possible in the sand casting. So green sand mold, it is just a mixture of sand, clay and water. And the green term is used because it is just referring to the fact that the mold is moist or damp while the metal is being poured into it. This is the least expensive among the other type of molds, sand molds. And the sand here can be recycled and therefore reused. In the cold box mold process, organic and inorganic binders are blended into the sand to bond the grains of the sand chemically for a greater strength. So these molds, they are dimensionally accurate, more dimensionally accurate compared to green sand molds. But of course, because of the fact that we are using binders, this is more expensive compared to green sand mold. And this is a cold setting process. That means the sand is set without any heat. The other cold setting process is no bake molds. Of course, the name also implies that. And in the no bake mold process, again a synthetic liquid resin is mixed with the sand, and it helps the mixture to harden at room temperature. Therefore, we don't need to use heat to set the mold. Generally, sand molds can be oven dried, or we call it baked, prior to pouring the molten metal. Of course, this makes it stronger and provide better dimensional accuracy and surface finish to the casting. So what are the major components of molds in sand casting? So let's talk about these on the figure actually. So here I need to mention, you guys need to, I can ask, for example, give this image, and I can ask a certain part, what is the name, and put an arrow to that part, and you should be able to tell me and choose the correct answer from the multiple choice. What is the name of that feature basically we are using in sand casting? All right, so the flask here. Flask. This is to support the mold itself. And mold will have two pieces. Cup on top, this one, right? And then drag on the bottom. And in between the seam between cup and drag is parting line. There is a pouring basin, and that is also called the cup. And of course the sprue through which the molten metal flows downward by gravity, and the runner system, okay, which has channels that will carry the molten metal from the sprue to the mold cavity, and gates are here, are the inlets to the mold cavity, and there are risers which supply additional molten metal to the casting as it shrinks during solidification. There are blind risers and open risers. Blind risers are within the, it is not open to outside, this is inside the mold. And there are cores. The core are inserts made from sand, and they are placed in the mold to form hollow regions. So if you have hollow regions that you need to form inside your cast, then you should put a core before actually pouring of the metal. So this can also be used on the outside of the casting to shape features like lettering and numbering. And there are vents. Vents are necessary because they will carry off the gases produced when the molten metal comes in contact with the sand in the mold and the core. Basically, they also exhaust air from the mold cavity as the molten metal flows into the mold. So what are patterns? Patterns are used to mold the sand mixture into the shape of the casting. So they can be made from wood, plastic, metal, or any combination of materials. And their selection will depend on the size and the shape of the casting, dimensional accuracy or quality of the casting, or the molding process. And the patterns can be used repeatedly to make the molds. Therefore, their strength and durability is very important when you are selecting the material to make the pattern. In designing the pattern, we need to be careful in certain things. One of which is the design of the pattern should provide for metal shrinkage and also permit the proper metal flow into the mold cavity. And it should also allow the pattern to be easily removed from the sand mold. This is achieved with the draft angle, as we're gonna see in the image here. So you are seeing a comparison of poor and good pattern making. The pattern, if it has not providing a draft angle, so this one is like that, this one is like that, it's tapered, right? So that type of design of the pattern will provide, will make the removal easy, removal of the pattern from the mold easier. Therefore, always there is a draft angle in the design. So cores are internal cavities or passageways, and these are the example, you can find them in engine blocks or valve bodies. We need to place a core into the mold cavity to form the interior surfaces of the casting. Like molds, the cores also must possess strength, permeability, collapsibility, and the ability to withstand heat. And they are made of sand aggregates. They are made of sand. And so there is there needs to be a way to anchor those cores into the mold. The core is anchored by what we call core prints. These are geometric features added to the pattern in order to locate and support the core. So if you look at the image, we're gonna see. So these are the core prints here that are basically holding the core so that it doesn't move around when we are pouring the metal. So there are also chaplets. Chaplets are again to keep the core from moving around, shifting. Metal supports, those are called chaplets. They can be used to anchor the core in place, and then we are seeing that in here, right? Because we don't want this core which are forming the inner surfaces of your part, we don't want this to move around during the pouring of the metal. So that's why they need to be anchored inside the mold. So how do we mold the sand? So the common way is compact the sand by hammering it around the pattern. But now there are machines, molding machines that can eliminate the labor, offer high quality casting, and increase production rate. So what is vertical flaskless molding? In this case, as the name implies, it's flaskless. The halves of the pattern form a vertical chamber wall against which sand is compacted. Halves are packed horizontally, and this eliminates the need for flask. It has high production rates, and sand slingers are used to fill the sand uniformly because it has a high pressure stream of the sand. And we are seeing the image of a sand slinger here, how sand is being introduced to form the mold. It introduces the sand at high speeds and therefore sufficiently pack the sand. So let's see the image of this molding process. Here again, figure 11.7, we are looking at vertical flaskless molding. So sand is squeezed between two halves of the pattern, and as you can see, assembled molds pass along on an assembly line for pouring. And then we are seeing actually a photograph of a vertical flaskless molding line. So you remember what the flask is. These are the metal supports that are holding the sand in place. And in flaskless molding, we don't need that because here the molds are supporting each other and forming vertical molding process because we are pouring the metal right there, right? So this part of the mold cavity comes up next to the other part of the mold cavity, so they combine and together they form the vertical flaskless molding. And there is also impact molding, and as the name implies, the sand is compacted by a controlled explosion or an instantaneous release of compressed gases. And of course, this will produce a mold with uniform strength and good permeability. So here is the vacuum molding process. And there is a plastic sheet which was placed over the pattern in the figure A we are seeing. And with the help of the vacuum, the plastic sheet is taking the shape of the pattern. A flask is placed over the pattern and is then filled with dry sand. A second sheet of plastic is then placed on top of the sand, right there, shown with the blue. And of course, a pouring basin and a sprue is inserted. Both halves of the mold are made in this manner, cop and drag, remember. So one of them is made and the other one is then again made, and then this will provide us the both halves of the mold, and then we assemble this both halves together, right? And during the pouring of the molten metal, the mold remains under vacuum, you can see. Okay. But the mold is under vacuum, not the casting cavity. And when the hot metal has solidified, then the vacuum is turned off, the sand falls away and releasing the casting. So that vacuum is holding the sand together in place. The vacuum molding does not require a draft in the part, and it is economical because of low tooling costs, long pattern life, and absence of binders in the sand, which basically the sand can be reused over and over again. Meaning over and over again means you damage it to remove the part, but then you can reuse it to make the mold. Now we're gonna take a look at the sequence of operations for sand casting. So first we need a mechanical drawing of the part that is gonna be used to generate the pattern. So this is like what we want, okay, that's our desired part. So of course, when you are doing this design, you need to be careful about incorporating the information of shrinkage and draft. Remember for easy removal, etc. So to make the cup and drag, so two sides of the mold, remember, we need their pattern. So those patterns are prepared at B and C, we are seeing. And with the presence of the gate, of course, and the core prints. Core prints, remember, holding the pattern in place. And the gate, which allows the flow of metal to the cavities. So core boxes are producing the core halves, which are going to be pasted together, and the core, remember, will be used to produce the hollow part of the hollow area of the part, right? So the cup half of the mold is assembled by securing the cup pattern plate to the flask with aligning pins and attaching inserts to form the sprue and risers. Okay. So the flask is rammed with the sand and the plate and inserts are removed. The drag half is also produced in a similar pattern. The pattern flask and the bottom board, they are inverted and the pattern is withdrawn, leaving the appropriate imprint. The core is set in place with the drag cavity, and the mold is closed by placing the cup on top of the drag and securing the assembly with pins. After the metal solidifies, the casting is removed from the mold. The sprue risers, these are cut off and can be recycled, and then the casting is cleaned, inspected, and heat treated if necessary. So now we have learned so far sand casting, right? Now we will learn shell molding. So we can explain each step when we are looking at the figure, but this technique provides close dimensional accuracy, good surface finish at low cost, and small mechanical parts such as gear housing, cylinder heads, and connecting rods can be produced. Complex shapes are possible, and sand has much lower permeability than the sand for green sand molding, and the cost increases due to the resin binders and metal patterns. So the shell molding process, shell mold casting, this is also called dump box technique. Mounted pattern of a ferrous metal or aluminum is heated. The mold is actually a thin-walled shell obtained by applying this sand resin mixture around the pattern. This pattern is coated with a parting agent. The parting agent, usually is silicone, is used so we can easily remove the part. So that is attached, that pattern is attached to a box or chamber, this one attached to it. That box contains fine sand mixed with thermosetting resin binder, which coats the sand particles. So what happens is then the box is rotated upside down and the sand mixture is blown over the pattern. So this is your pattern, which was in heated metal. The sand that has the mixture of the sand and the with the thermosetting resin binder, they are now taking the shape of the pattern, basically. So the pattern and the shell removed from the dump box. So the shell is a thin layer, thin-walled shell is obtained when we apply this sand and resin mixture around the pattern. Again, the mold halves, they join together with clamps. after this is actually the mold is placed in an oven to complete the curing of the resin. Remember, it is thermosetting resin, and then we need curing. Curing means formation of those cross links, so the material becomes stronger. It is then placed in a flask and metal is poured basically. So much smaller grain size, sand grain size is used in shell molding compared to green sand molding, which of course, as we talked about, lowers the permeability. And also the binders will decompose, which will produce high volume of gas. So we need proper ventilation of the system to remove those trapped air and gases that can produce defect in the castings. In this case, the shells are very light and thin, as you can see, and the thickness of it can be determined by controlling the time the patterns are in contact with the mold. So of course their thermal characteristics will be different than those for the thicker molds. Alright, next is plaster mold casting. These processes are known as precision casting, together with ceramic mold and investment casting processes, because they have high dimensional accuracy and good surface finish obtained on the parts that we cast. So in the plaster mold casting, the mold is made of plaster, which is the mixture of gypsum, lime, or cement. So components are mixed with water to create a slurry. Slurry is poured over the pattern and the plaster sets. Then we remove the pattern and we dry the mold at around temperatures between 120 degrees C to 260 degrees C. Then we, of course, as we always do, assemble the mold halves, and then the molten metal is poured into the mold. So these are the basic steps, and typical parts we obtain with plaster mold casting are gears, fittings, tooling, ornaments. Plaster molds have very low permeability. So that means the gases that is evolved during the solidification process cannot escape the metal. Therefore, the molten metal is poured either in vacuum or under pressure to prevent the defects forming due to the presence of gases. Patterns for plaster mold casting, they are made of aluminum alloys or thermosetting plastics, and it can be also brass or zinc alloys. So of course there is a limit to the maximum temperature that the mold can withstand. It is generally about 1200 degrees C. Therefore this
casting technique is only used for low melting point metals like aluminum, magnesium, zinc, and some copper-based alloys. The casting have a good surface finish, but because the blaster molds have low thermal conductivity compared to other mold materials, remember it was very important to the rate of heat removal from the solidifying metal, because it affects the characteristics. And the blaster molds have lower thermal conductivity, therefore the casting will cool slowly. Slow cooling will create a more uniform grain structure. Ceramic mold casting, also called cope and drag investment casting. This is similar to plaster mold casting, except in this case refractory mold materials are being used, which they can withstand to high temperatures. So first a slurry is made from the mixture of zircon and aluminum oxide, fused silica, and other bonding agents. So all those materials are refractory and can withstand high temperatures. This is again a precision casting, meaning it will provide high dimensional accuracy and good surface finish. So once you have a high dimensional accuracy in a casting, it prevents you, it basically eliminates the need to further machine the part, which is economically much more preferred, right? Extra processes are not desired. So what type of parts can be made? Impellers, cutters, dies, molds for casting plastic and rubber components. These are possible parts that are made by this technique. This technique is used for casting for ferrous alloys and high temperature alloys, stainless steels, and tool steels. Okay, so here are the steps in this process, but as I always tell you, please watch the videos I'm sending you. And here first we have the flask and the pattern inside. The prepared ceramic slurry is poured, and so after removing the mold from the flask and the pattern, it is actually needs to be dried, so it's wet. That's why it's called green. And when we remove it, we need to remove the volatile matter, and therefore it has to be baked. Here in the image they are using torch to do that. It is also possible. So then the molds are then clamped and basically used as molds in the casting of these metals. This process is expensive but can be used in the production of a wide range of sizes and complex shapes. So now we're gonna take a look at the expandable mold and expandable pattern casting processes. So in this case, both the mold and the pattern has to be produced for each casting. Okay, the first one is lost foam or evaporative pattern casting. This technique is using a polystyrene pattern, which evaporates upon contact with the molten metal to form the cavity. This technique has become an important technique to cast ferrous and non-ferrous metals. So how we make the patterns out of polystyrene? The polystyrene beads, they are placed in a preheated die that is usually aluminum, made out of aluminum, and then complex patterns can be made. The polystyrene beads, when they are placed into the preheated die, they expand and take the form of the pattern. The die is cooled and then opened, and we remove the polystyrene pattern. And then the pattern is coated with water-based refractory slurry and dried and placed in a flask. The flask is filled with sand, and this supports the pattern. And then the molten metal is poured into the mold, and of course this vaporizes the pattern, which was made out of polystyrene. And then the metal completely replaced the space that was previously occupied with polystyrene. But of course, when there is a phase change like that from evaporating of a polystyrene material, you need to provide energy to it, right? That's why the polymer requires energy to degrade. Therefore, it affects the cooling characteristics of the metal. So metal cools faster than it would if it was poured directly into an empty cavity. So therefore it will cause the microstructure to be different than what is we observe with just regular casting techniques. This technique has advantages over other casting techniques. First, it is simple. There are no parting lines, cores, or risers, and the flax used for this process is inexpensive. And polystyrene is inexpensive and can be used to create complex shapes in various sizes and fine feature details. And after this, further finishing and cleaning operations are minimum. So in this figure, we are seeing each step that I just described. First, you obtain the pattern which was made out of the polystyrene. It can be assembled to clusters, so this way you can produce multiple parts at the same time. Then remember, we coat the pattern with the water-based refractory slurry and then place it in a flask and fill it with sand and compact the sand. And then we pour the molten metal. Which we do without removing the polystyrene. And after that, the polystyrene pattern vaporizes and metal fill the mold cavities. And then, as you can see, when we shake it out, and we obtain the parts. That is how simple this process is. Here we are seeing the actual images from a foundry. During the lost foam casting, the metal is being poured into the mold, and some products that has been produced with this technique, such as a motor and a finished engine block. Okay, so investment casting process. This is also called lost wax process. So in this case, the pattern is made of wax or of plastic. And again, the plastic can be polystyrene. So it is similar to the previous technique. So after we make the pattern, then the pattern is dipped in a slurry, again of refractory metals. And you can join multiple patterns like the previous technique, and this is called a tree. So in this technique, it requires labor and material. They are high cost, but you can cast high melting point alloys with a good surface finish. Here each stages of this technique illustrated. First we need to make the pattern out of wax or a plastic, and we do that and we assemble it. We call it tree, right? We put multiple of them together, and then we dip it into a slurry, and then this coats the pattern. So to increase the strength of the coating, actually the pattern is repeatedly dipped into the slurry. Once we complete the mold, now we need to remove the pattern. It will be just melted out like you've seen in stage 7. This time we initially melt the wax out before we pouring the metal. So then we pour the metal and then shake out the mold, and we can remove the casting, and we can also recover the wax and then reuse it again to make the patterns. Alright, in this figure we are seeing investment casting of a rotor for a gas turbine. First there is the wax pattern in the image A, and then the shell is coated over that wax pattern in image B, and the wax is melted out, and then the mold is filled with molten metal, which is a super alloy in this case, because that's what we use for gas turbines. And at the end you are seeing the cast rotor, and that is nearly the same shape as the initial pattern. So here we are seeing progression of the tree, and here we are seeing it is assembled and then coated at image B with the sand, and then of course after the removal of the mold it looks like as in image C. Now all those processes we have seen so far, they were expandable mold processes. And now we're gonna see permanent mold casting. As the name implies, we are reusing the mold here, and the mold, they are made of cast iron, steel, bronze, graphite, refractory alloys, and that's why they can be used again and again, because these materials have high resistance to erosion, thermal fatigue. That's why these are permanent molds. Okay, so what type of parts that are being produced with the permanent mold casting? Automobile pistons, cylinder head, connecting rods, gears, appliances, kitchenware. So because we keep reusing the mold, we need to make sure we increase the life of the molds. So the mold cavity and the gating system here are machined into the mold, and they become the integral part of the mold. So of course, if you want to produce internal cavities, you can use cores, and the cores can be made of metal or a sand. And of course they need to be placed prior to the casting into the mold. Okay, so we were talking about how to increase the life of the molds. In this case, the mold cavity surface can be coated with a refractory slurry. This can be also graphite with every few casting. So these coatings can serve as parting agents and also as thermal barriers. And this can control also the rate of cooling of the casting. Well, although the equipment costs are high in this process because die costs high, but the labor costs, they are kept low because of automation. It is not an economical process for small production runs, and it is not suitable for intricate shapes because of the difficulty of removing the casting from the mold, because always you need to think about how easy it is to remove the cast from the mold. And in this case, so since these are permanent molds, we cannot shake them, and it is difficult compared to expandable mold casting. Therefore, complex shapes might not be possible. This process is used mostly for aluminum, magnesium, copper alloys, gray iron, and steels can also be cast using graphite or other heat-resistant molds. This technique provides casting with good surface finish and close dimensional tolerances, uniform and good mechanical properties, and it can produce parts at a higher production rates. So what is the process here? Molds are clamped together mechanically, and the mold is heated to aid the metal flow. And you guys know the fluidity of the metal is very important, and this also reduces the thermal damage, because if the mold is kept at lower temperatures, as you keep pouring the hot metal, it will be exposed to thermal shocks, and we don't want that. We don't want to damage the mold. Metal is then poured, and after it solidifies, water is used to cool the mold, and mechanical ejector pins are used to remove the part. So vacuum casting, this is suitable for particularly thin-walled complex shapes. And typical parts made are superalloy gas turbine components with thin walls. In this process, as you can see, we have an induction furnace, and inside the furnace we have the molten metal. A mixture of sand and urethane is molded over metal dies and cured. So the mold is then held with a robot arm here, and this is immersed partially into molten metal which was in the induction furnace. Well, the vacuum is then reduces the air pressure inside the mold, and this will draw the molten metal into the mold cavities through the gate, and this process can be automated with production costs that are similar to those of green sand casting. So what type of metals we can cast with this technique? Carbon low and high alloy steel, stainless steel parts can be produced with this technique. Other metals are also possible to produce with this technique. It's aluminum and titanium, zirconium, hafnium. So slash casting, in this technique we can create hollow castings with thin walls. So in this case, the molten metal is poured into the metal mold, and after the desired thickness of the solidified skin is obtained, the mold is inverted and the remaining liquid metal is poured out. And then, of course, the mold holes, they are open and the casting is removed. So slash casting is suitable for small production runs, and they're generally used for making ornamental and decorative objects such as lamp bases, stems, toys from low melting point metals like zinc, tin, and lead alloys. In pressure casting, the molten metal is forced by pressure into a graphite or metal mold. The pressure is maintained until the metal has completely solidified. It can also be forced upward by a vacuum, which then removes all dissolved gases and produce a casting with lower porosity. Pressure casting is generally used for high quality castings like steel railroad car wheels, and these wheels can also be cast in sand molds and molds made out of graphite and sand. What about die casting? So typical parts made by die casting, these are housings for transmission, business machine and appliance components, hand tools and toys. This process should not be confused with the pressure casting, because in this process we use very high pressures, typical pressures ranging from 7 to 350 megapascal. The pressure is maintained during the solidification, after which the mold is opened and the part is removed. Molds that are used in this casting operation, they are called dies. That's why the name die casting comes from. So the use of high pressure to force the metal into the die cavity is the most noticeable feature of this process that distinguishes this process from other permanent mold casting techniques. There are two main types of die casting machines, hot chamber and cold chamber, which are differentiated by how the molten metal is injected into the cavity. So in hot chamber die casting, basically the metal is melted in a container attached to the machine, and a piston is used to inject the liquid metal under high pressure into the die. And the pressures in this case goes up to 35 megapascal. This process is suitable for low melting point metals because the parts that are involved in this technique is they are submerged into the molten metal. Therefore, we don't want them to degrade the metals that are being used in the production. Therefore, the low melting point metals and the metals that do not chemically attack the mechanical components can be casted. These are zinc, tin, lead, and sometimes magnesium. So this is the illustration of the hot chamber die casting process. We are seeing the plunger, and here the metal is held under pressure until it solidifies in the die. So to improve the life of the die and allow rapid cooling of the metal, dies can be cooled by circulating water. The injection mechanism of the hot chamber machine is, as you can see, immersed into the molten metal. So you see within the pot, and the pot is attached to the furnace, we have the molten metal. And plunger pushes the molten metal through the nozzle into the die cavity, which it's held under pressure until it solidifies. Then the die opens, and basically with the use of ejectors, the part is removed from the die. When the plunger returns to its original position, it allows the residual molten metal to flow back through the nozzle. In cold chamber die casting, the molten metal is poured into an unheated chamber from an external melting container, and the piston is used to inject the metal under high pressure into the die cavity. So typically the pressures can go up to 70 megapascal. This process is used for casting aluminum, brass, magnesium alloys. So the die closed and the molten metal is poured into the chamber. And the plunger is forcing the metal to flow into the die,
maintaining the pressure during cooling and solidification. And then the plunger is withdrawn, the die is open, and the part is ejected. In this table, we are seeing the properties and typical application of die casting alloys like aluminum, brass, magnesium, and zinc, and what are the applications they are being used, in what applications they are being used, and some properties like tensile strength, yield strength, and elongation, so ductility. So I should mention in die casting, the molds are made of tool steel, mold steel, miraging steel, and tungsten and molybdenum with good refractory qualities are being used. And dies can be single cavity or multiple cavity, as you've seen in these images. To remove the part always from the die, when it opens up, we need ejector pins to push them. And so when the pins pushing them away from the mold surface, it can be removed, but also lubricants are sprayed into the cavity so we can prevent the sticking of that metal. There are also combination cavities, so several different cavities within the mold, that is also possible. And there are also unit dies. The whole unit is casted at once. Here we are seeing basically an image of a die cast aluminum part. Okay, centrifugal casting. So this is another type of permanent mold casting process. And as the name implies here, we use centrifugal forces to distribute the molten metal into the die cavity. There are 3 types of centrifugal casting: true centrifugal, semi-centrifugal, and centrifuging. In true centrifugal casting, the molten metal is poured into a rotating mold to produce a tubular part. So some examples made by this process: pipes, tubes, rings. So to get this some idea here, you can see there are rolls that are being used to rotate the mold, and we are seeing in from different directions the same thing. So you see the molten metal is poured, and then basically high-speed rotation results in centrifugal forces to get the metal to take the shape of the mold cavity. So in true centrifugal casting, the molds are made of steel, iron, and graphite, and may be coated with the refractory lining to increase the mold life. But because of although the molten metal is uniformly distributed by the centrifugal forces, of course, due to the presence of density differences, lighter metals like impurities can collect on the inner surfaces of the casting, which can result the change in properties throughout the thickness of the cast. So in semi-centrifugal casting, again the centrifugal force is used to produce this time solid casting rather than tubular casting. The method is used to cast parts with rotational symmetry, such as a wheel with spokes.
So again, the same problem here. The density of metal in final casting is greater in the outer sections compared to the center. Therefore, this process is often used on parts in which the center of the casting is machined out. So basically, we are eliminating the portion of the casting where the quality is lowest. So the schematic of the semi-centrifugal casting process. Wheels with spokes can be cast by this process, as we talked about. There is the revolving table rotating and creating the centrifugal forces. And the metal is poured from the middle. And as you can see, it is a part with a rotational symmetry which is being casted. What about centrifuging? Okay, centrifuging. The mold is designed with part cavities located away from the axis of rotation so that the molten metal poured into the mold is distributed to those cavities by the centrifugal force. And this is used for small parts. And the radial symmetry of the part is not a requirement as it is for the other two centrifugal casting method. And we see that image in image B here. This is the illustration of casting by centrifuging. And you see the molds are placed at the periphery of the machine. And the molten metal is forced to the mold cavities by the centrifugal force. Squeeze casting is a combination of casting and forging. Right now, when you say forging, think about hammering a metal, okay? It is a combination of casting and forging in which the molten metal is poured into a preheated die, lower die, and then the upper die is closed to create the mold cavity after solidification begins. And if you take a look at the illustration here for the squeeze casting process, we see the lower die cavity and there is the upper die, right here and here, and molten metal is poured into the die here, and the upper die is closed to create the mold cavity after solidification begins. And then with the use of ejector pins here, we are pushing to remove the cast. So this differs from the usual permanent mold casting process, where the die halves are closed prior to injection. In this way, in this one we close it after we pour the metal. Of course, here the required pressures that you need to apply is much less than the forging process that we know, where we are basically working on a solid metal. And this technique can be used for ferrous and non-ferrous alloys, aluminum, magnesium, mostly used in automotive industry, automotive components. So this technique results in fine microstructure because there is more contact of the die with the metal, and this of course removes the heat more rapidly. And remember, when the heat is removed more rapidly, you end up getting a fine microstructure and therefore good mechanical properties. Well, the composite mold casting, remember we learned about permanent mold casting, expandable mold casting, and there was also composite mold casting, which is basically two or more different materials can be used to prepare the mold, like plaster, sand, metal, graphite. This way you can change the properties of the mold. You can get better strength, improve dimensional accuracy and surface finish. And this will of course reduce the cost and time because you don't need further processing of the part. And casting of complex shapes possible with this technique. And you can adjust, as we talked, the rate of solidification. You can control it, because you are controlling the properties of the materials that are used in the construction of the mold. Now all those materials that we have learned how to cast, those materials are usually polycrystalline structure. But what about when we used to cast single crystals, like the ones used in gas turbine blades for nickel-based superalloys? So how can we cast them? If we just do the casting of a turbine blade with just regular casting techniques we have learned, when the structure is polycrystalline, this makes it susceptible to creep and cracking along the grain boundaries under high temperature conditions. So therefore techniques developed to produce the turbine blades in a single crystal form. So one of them is directionally solidified blades. In this technique, the ceramic mold is supported by water-cooled chill plate. The ceramic mold is preheated. And then after the metal is poured into the mold, chill plate assembly is lowered slowly. Crystals will begin to grow at the chill plate surface and will move upward, like the columnar grains we learned about. This way the blade is solidified directionally with longitudinal but no transverse grain boundaries. This way it makes the blade stronger in the direction of centrifugal forces that are developed in the application of it, in the operation of it in the gas turbines. So to understand that, let's look at the illustration of this process. So this is the directional solidification. You have a chill plate and ceramic mold which holds the molten metal, and then the chill plate is lowered down slowly, and this makes the grains, of course, grow along one direction like that. Basically, you are playing with the direction of the heat flow. Remember, it was also responsible for formation of columnar grains in a casting. In the process of single crystal blades, here the mold has a constriction in the shape of a corkscrew or helix. So the cross-sectional area is so small that it only allows one crystal to fit through. So the most favorable or oriented crystals will be able to grow through the helix. The rest will be intercepted by the walls of the helix. Look, there's a figure here. We can see how this is happening. It is the same way, but there is this helix in between the
ceramic mold and the chill plate, which only favorable ones will be able to move through and reach go through the helix. The assembly is slowly lowered like the previous example, and then the crystal will grow upward through the constriction, and this technique is actually expensive, but because this is a single crystal material that you obtain at the end, which doesn't have grain boundaries and makes them resistant to creep and thermal shock. Therefore, the parts will have a longer and more reliable service life. So what have we learned? We have learned so many things, right? We have learned expandable mold, permanent pattern processes like sand mold casting, shell mold casting, plaster mold, ceramic mold casting. Each time the mold was destructed, so we cannot reuse it. Again, we can use the pattern though because it's permanent. And expandable mold, expandable pattern, both the pattern and the mold cannot be reused, they are destroyed. We have also learned permanent mold processes, in which the dyes and molds, they can be used again and again, and this of course provides high production rates. And types of permanent mold processes are slash casting, pressure casting, die casting, and centrifugal casting. So the molds that are used in permanent mold casting, we said they are made of graphite or metal. And the difference between the expandable mold and permanent mold casting is the metals that are used to make the molds they are good heat conductors. Remember, the heat conduction affects the cooling rates, and therefore it will change the structure and therefore the mechanical properties of the metals. Also, unlike sands, these materials don't have pores, so it doesn't allow the gases to escape. So we need to be careful that we are removing the gases from the solidifying metal. So the die and equipment cost is high in permanent mold casting, but in large production runs this is more economical, because at the end you initially pay a lot of money to die and the equipment cost, but if you have large production runs you earn, so it compensates it. And we end up with getting metals with good surface finish and high dimensional accuracy, which further makes it more economical to further process and machine the parts after the casting is done. We have also learned squeeze casting and the casting of single crystal components.